Hello everyone, my name is Sohail. Today I'll be presenting a framework for property-based testing of robots and simulation, with a particular focus on tabletop manipulation for a domestic robot. My co-authors for this paper are Alex Mitrevski, Hochgeschwender, and Plöger, and I will be presenting on their behalf. This paper is motivated by the fact that before a robot can be deployed in any practical application, it is of interest to know whether it can perform its actions with acceptable safety and reliability. This aspect becomes particularly relevant as robot policies are acquired using learning-based methods, for which we often don't have sufficient formal guarantees of correctness. One way in which robot behaviors can be verified is using extensive testing. However, real-world tests are generally difficult or expensive to set up, while simulated tests are often handcrafted or limited in scope. Keeping in mind the challenges faced by a domestic robot and the traditional approach of dealing with it, our research paper addresses the question of how to test a robot's behavior for systematic analysis in varied execution scenarios. We are interested in an approach that goes beyond software failures and encompasses real-world interactions. We divide our research question into two parts. We are first interested in dynamic and robust scenario generation. We are also interested in qualitatively and quantitatively testing our robot so that we can answer questions such as what is the cause of failure, as well as where, when, and how did it fail. Our proposed framework for solving the research questions is by means of property-based testing, in which we generate a set of simulated scenarios in which a robot performs a task and assesses its actions by using predefined property-based tests. The presented figure illustrates the working of our proposed framework. The cycle starts from a test configuration, in which scenarios are defined and generated, which are then fed into a property-based test suite. The property-based test suite then utilizes both an action ontology and a test configuration to set up a variety of tests which it verifies via the robot architecture and robot middleware. This cycle may be repeated indefinitely. At the end of the cycle, a report is generated that has the result for all the tests. In this work, we will not be discussing the robot architecture nor the robot middleware. We will start by describing property-based testing. We will then discuss the action ontology. Then we will move on to the test configuration. Lastly, we'll explain test report generation. Property-based robot testing is a testing framework in which we design tests around a system's properties and ascertain whether these properties are satisfied or not. This has four main requirements. First, modeling the system and its expected behavior. Second, determining the allowed range of input parameters for the tested components. Third, generating input parameters. And fourth, validating the expected behavior of the system. The shown figure demonstrates an example of applying property-based tests in context of picking up an object. Through the combination of the shown property tests, different types of failures can be identified. For example, the success of property 1 and 2 and failure of property 3 would mean that the robot picked an object, but the object did not remain between its grippers and fell down onto the floor. In the action ontology, we define an association between a robot's action and the properties that define the action's success. Each of these associations are modeled using the web ontology language OWL. We define various properties in ontology such as performed in relates an action of a robot to the coordinate frame in which the action is performed. Success property describes the properties to be tested within a given action. Has parameters and need parameters are the requirements which have been predefined for an action and a property respectively, both of which are based on the context of an action. In test scenario generation, we generate a variety of scenarios by spawning objects in different locations using the Monte Carlo method. Each object has been manually designed, allowing us to introduce varied aspects to the object, such as change size, shape, mass, and inertia. To ensure that the items do not spawn on top of each other due to randomness, we utilize the axis-aligned bounding box approach, which is a fast and efficient method of determining valid spawn locations. An example of the scenario generation using the axis-aligned bounding box method is given in the presented figure. To add more control and flexibility to the scenario generation, we enable the parameterization of scenarios via test scenario configuration. The presented table shows a subset of the parameters that can be configured for scenario generation. Through these, we are able to determine the number of objects that could be spawned, the type of objects, the world environment, the type of scenario, and so on and so forth. The test scenario configuration narrows down our test domain to what is required, making it feasible enough to perform exhaustive qualitative testing. In the test report generation, we store all the important data, including the test scenario configuration, in an HTML format as shown. The presented figure illustrates a report for a failed point-to-point navigation run, in which the navigation goal could not be reached due to an obstacle standing on top of it. Additional details that are stored are the description of the tests, consistencies, word properties, and various other parameters. The framework is once again summarized for convenience. We feed the property-based test suite with a test configuration and an action ontology from which scenarios are generated. The success of the robot's actions is then assessed in those scenarios. We now present a single pick-and-place run, which is a combination of multiple actions, namely navigation, perception, object grasping, and object placement. On the top left, we see the detailed view of our proposed architecture. Currently, the robot has navigated towards the table, has perceived the table, and is now performing a pick action. Once the cup is picked, it will now begin planning a trajectory to place the cup back onto the table. Once the cup is placed, the robot will retrieve its arm and the scenario will terminate, after which a report will be generated. All of this is guided by the property-based test suite. The presented chart visualizes the result of the pick-and-place task. The x-axis on the chart has the property test definitions, while y-axis denotes the number of scenario runs. The yellow bar indicates incomplete test, which was a frequent result due to the desynchronization of ROS messages. What this means is that when the communication server would send a message, the robot would not receive it and remain stuck indefinitely. As illustrated in the chart, the majority of the object pick-and-place runs ended with incomplete or failed results due to the ROS desynchronization, object collisions, or trajectory planning failures. It is clear from the chart that the more actions the robot has to perform, the more the risk of failure increases. It should be noted that the objective of the evaluation of the test case scenarios was to discern whether the approach of property-based tests could successfully and consistently verify failed scenarios and if patterns could be identified. The main outcome of this work are that, firstly, the property-based test approach, in combination with parameterized and randomized scenarios, is able to consistently identify failed actions, even when the actions were considered a success by the robot's trajectory planner. Secondly, by the parameterized and randomized scenario generation, we were able to repeatedly test the robot in a variety of diverse scenarios, identifying common failure patterns. Thirdly, leveraging the simulator's information of the absolute state of the world is an advantage of the approach, as it enables the testing of various action properties. In summary, the contribution of this work is the proposition and demonstrated implementation of property-based test as a robust tool for verifying a robust action. There are various requirements that affect the practicality of the proposed approach, such as a powerful hardware to perform repeated and speedy simulations for the property-based tests, a fully developed and matured robot system, time for identifying relevant properties to be tested, and ensuring the software interfaces on the real robot and in simulation are as close as possible to each other. Thank you for your attention. Also special thanks to the BIT Foundation and the Sesame EU project for funding this work.